Let's jump into it. All right, so this demo is on speed of light, okay? But before we get into it, you guys know that waves, right? Like light is a wave, yes? You guys know that, right? Light that you see outside is a wave. Radio is a wave, right? TV is actually a wave, right? So there's actually two types of waves. There's electromagnetic waves, and then there's mechanical waves. So all waves you can categorize to just two, okay? What's the difference? These guys can go through vacuums, okay? But mechanical waves, they need like a medium, like sound, right? I'm talking to you right now, you hear me. Why? What's carrying the sound? What's in this room that's carrying this? You know, remember I said it needs a medium, right? What medium do you think the sound is carried over? I'm talking to you, I'm making a noise. You hear it. So what medium carries that sound to you that's in this room? That might not be in outer space. Yeah, you're right, yeah. So air molecules, right? So these guys need mediums. They need mediums, okay? So sound, ocean waves need a medium. What's the medium on ocean waves? What carries the ocean waves? Water, yeah. So these guys, on the other hand, don't need mediums. They can go through vacuum. And you know they can go through a vacuum because look at the sun. Sun, has, light comes from the sun, right? And here's the earth, and here's the atmosphere, right? Here's the atmosphere around the earth, right? But is there any air molecules here? From sun to here?
No.
No, but the light is, you're able to see the light from the sun because it's the electromagnetic wave that can go through pretty much anything, even a vacuum. Does that make sense? Okay. Now let's, now that you know basics about the two types of waves, let's jump into the reading. Go ahead, Richard, why don't you start us off?
Nuclear chocolate and measure speed of light. Fundamental physics constant. Remember E equals mc squared? Einstein's famous equation. The C stands for the speed of light. You don't need fancy equipment to measure it. All you need is a microwave, ruler, bar of chocolate, and a calculator.
Yeah, go ahead. Maybe one of you ladies can read the introduction.
Introduction. Anyone can measure the speed of light, C. The speed of light is equal to the wavelength multiplied by the frequency of an electromagnetic wave. Microwaves and invisible light are both examples of electromagnetic waves. Speed of any wave can be found by using the formula V equals F.
Yeah, so let's stop right there. So you guys know, you've heard of this equation, right? Einstein's famous equation, right? What does C stand for?
Speed of light.
Speed of light. Now, speed of a wave, I can find it using this formula that says velocity or speed of any wave, in this case light, right, is equal to something called frequency times wavelength, okay? So if I know frequency and wavelength, can I find the speed of the wave? Yeah, I could, right? Because all I need is these two things. Okay, so let's read about what frequency and wavelength are. Go ahead. Maybe the middle school child, let's go.
When you turn on your microwave oven, electrical currents inside the generated microwaves,
Electromagnetic
waves and frequencies around 1.25
gigahertz. Yeah,
gigahertz.
it's a.
These waves bounce back and forth between the walls of the oven. The
Magnetic
field inside of the microwave behaves in roughly the same way as a guitar string, except for the vibrations or the electromagnetic.
Yeah. So frequency is the definition of frequency is waves per second. Is there you guys listen to any radio stations while you're in the car, right? What is your favorite radio station to listen to?
103.5.
Okay, at 103.5, but they say, what is it, megahertz or whatever. You see that on the radio, right? So see, radio, remember radio going back is a type of a, what wave? What type of wave is a radio? Electromagnetic, right? You see, electromagnetic waves, right? The frequency means the number of waves they have for 1 second. Okay, all these waves have different frequencies, like radio wave, different channel, 106.5 or whatever. you see, when you change the channel, you change the frequency, and it will pick up a different radio channel. So all these waves have a different frequency at which it vibrates, okay? So radio waves have different frequencies, microwaves have different frequencies, okay? And by the way, let's connect the microwave into the light, okay? So light is what type of wave again?
Electromagnetic.
Electromagnetic. And microwave is what type of wave? Electromagnetic still. So, and these waves, right, since they're both electromagnetic waves, they actually go at roughly the same speed, in air, or even in, vacuum, they go, I mean, over here, when there's a vacuum, they go faster, but they slow down a little bit, but that slowdown is negligible, so we don't count that. But yeah, they all roughly go about the speed of light because they are part of what? What type of wave? Electromagnetic waves, okay. So now if I know the frequency of the microwave, and let's say I find the wavelength of the microwave, what do you expect the microwave to go at then, if they're all type of electromagnetic waves? The same speed. By the way, what is the speed of light? What is c? Does anyone know? Richard, you should know. You had a physics reference table.
I agree.
I know we're not up to that part yet, but it's 300,000. Okay, 300,000 meters per second. Big number. Okay. Yeah. Okay. Okay. So let's read. Where it is, did we do the frequency? Yeah, we did do the frequency, right? Let's read the wavelength part. Okay. Go ahead, who's going to read it for me? Go ahead, Richard, why don't you read it?
The wavelength is the distance between successive crests of a wave. This value indicates how long one wave is. Wave speed v. Microwaves are a form of electromagnetic radiation and therefore travel at the speed of light. All electromagnetic waves travel at the speed of light. Reminder, light is also an electromagnetic wave since it is able to go through a vacuum. If you know the frequency of a microwave, finding out their wavelength will help you calculate how fast they are traveling.
Okay, so real quick. So wave speed, right? We skipped over the wavelength. A wavelength, what's the definition of wavelength? What's the definition?
A distance between successive crests.
Okay, so it's basically the length of one wave. So what's the length of, so if I start here, right, where does the one wave end? If I start here, is it ending in A, B, C, or D? Where if I start here, where is the one wave end? A, B, C, or D? Roughly that. Hi. Is that still? Yes. Okay. Go ahead. So while you guys get in that worksheet, if I start with here, right, where does the speed, the wave end? If I start from right here, where is this is one wave, right? If you start here, right? If you start here, where does the one wave end? Is it at one wave?
Yeah.
No, it's a half a wave. What about here? Is that a one wave?
No.
Where's that one wave end then? D. So that's called the. Okay, yeah. So wavelength is the length of the whole thing, yeah? From here to here. So let's read, did we talk about the experiment? Okay, let's talk about the experiment. Someone else read. Go ahead.
Experiment. Remove the turntable from the microwave so the plate does not rotate. Place chocolate scattered on a plate inside the microwave. Heat the chocolate until it starts to melt, about 20 seconds. There will be some melted hot spots and some cold spots in the chocolate. The distance between the melted areas is half the wavelength of the microwaves, or the distance between the anechoics. So, from this simple experiment and some easy math, you can work out the speed of light.
Yeah, by the way, I realized I made a mistake. It's 300 billion, right? Speed of light is not 300,000 meters per second, 300 million, okay? Please fix that. Okay, so roughly about, all right, so what we're doing is we're gonna get chocolate, right? We're gonna put a chocolate, and if I take the turntable out and heat up the chocolate, what do you think is gonna happen? What do you think the turntable doing in the microwave?
That creates a rotation.
So what does that do? If you want to heat up any food, why does it need to rotate while you're heating it up?
So the heat is not just hitting like one spot.
Yeah. Okay. So if I take the rotating table out and put let's say a chocolate, and the microwave is going through it, what's going to happen to it?
Certain parts will be melted for others, or
You see certain parts over here. What's going to happen to this spot and this spot? It will most likely melt, right? You probably see like maybe two like melted spots, right? What if maybe if we're lucky enough, you might even see this, right? How many melted spots would you see then?
3.
3, right? Depending on how the chocolate is. So that's what we're trying to do in this experiment. We're going to put a chocolate in the microwave, and we're going to take the plate out and let the microwave go through the chocolate, and we're going to see how many spots we see. And based on that, can I find the frequency and the wavelength?
Yeah.
Well, frequency we might have to find based on the microwave. How about the wavelength? Can we find the wavelength? Let's say I find that this distance here is, for argument's sake, let's say that this is 3 centimeters, roughly about. Then what is the wavelength?
3 centimeters.
Is that the full wave? Remember, the wavelength is the full wave, so that's what? Only what? Half. So what's the full wavelength? So it's roughly about what then? 6 centimeters, right? So I can say, oh, I know the wavelength, and if I know the frequency roughly about, I can plug it in and get the speed of the microwave. Does that make sense?
Yes.
Okay. All right. So let's try it. All right. So you guys can come over here and come around. I tried it with the other group. It didn't work the first time. I only saw one spot. So the second time it worked and I see the 2 spots now. Okay, but let's see if you get lucky. I have one more chocolate that might be good. So let's see if you get this time if you get a good result. Okay, but if not, we'll use there. Okay, you see how there's 2 spots right there? Take one here and like one there. You see that? Does that make sense? So if this doesn't work, and because right now I only have one chocolate, I'm down to one chocolate. So if this doesn't work, we'll use that here. Okay? Okay. Okay, so let's put it in for, you want to put it in for, see, there's no turntable. Turntable's out. Let's put it for maybe like 20 seconds, and then let's check after 20 seconds. There's a reset. Restart right now. I think that's a timer. Oh. Okay. Kind of see one right there. You see that? One right here? But we don't see the other one. Maybe it's
Like around here.
right around here, you think? Yeah, there's a little bit of spot right there. Should we put in more 4 and then maybe see if it becomes a little bit? Yeah, yeah, you see that too, right? Look, there's a little bit of spot, like if you look at the light, it's hitting right there, and maybe right there. Yeah? Let's see. It was at this angle, like we want to make sure it was like that, right? Okay. Let's put another 10 seconds. Okay. Yeah, actually, this is even better. Look, you see that, right? One here and one right there. Okay, we got lucky. Got it. Okay, so let's try to measure it now. Let's go back there and actually let's measure it using a ruler. What do you think it is? What's the wavelength? Let's pick the. You can't really pick the. Well, let's try to pick the center, right? So if you pick in the center of that and center of that, what do you think it is? Roughly about. 14 and a half, right? Maybe let's say 14, because there's no exact point. Let's say 14. Let's round it up. Okay, 14. But hold up, the wavelength should be in meters. So 14 is centimeters, right? 14 is only what? This part. Only this part, right? 14 is 14 centimeters this part. So what do you have to do?
Convert.
Well, before you convert, let's get the whole. What is the whole wavelength? If I'm starting here,
And then from 14, it would end up being 28.
28 centimeters. Now, that should be in what? Wavelength should be in what? Meters. So how do I convert centimeters into meters? Centimeters into meters, physics people. Well, unit conversions. Remember, you got centimeters here, and I want to go from centimeters into meters, right? So there's how many centimeters in 1 meter? 100, right? Remember, you need a reference table in front of you. Okay, there's 100 centimeters in 1 meter. So that means you divide 28 divided by 100 is about what? Roughly about. What is it?
That would be 2.8 meters.
Yeah, 0.28 meters. Now the frequency is funny because different microwaves have different frequency. Let's try to use the one that they have here. What's the one that? Okay, they have microwave frequency over here. It's not the same one. Usually I looked up the typical frequency of a typical microwave, but every microwave is different. Do you see the frequency over there? It should be in hertz or maybe even megahertz.
I see single phase microwave frequency 2,450 megahertz.
So megahertz, right? So 2,450 megahertz. If you remember, is 10 to the 6. Okay. So what they're saying is that the frequency of this microwave is 2,450 megahertz, right? Mega means, if you remember, is 10 to the 6. 10 to the 6. Mega is 10 to the 6, okay? Okay, so that's the frequency. So we know the frequency. Do we know the frequency now?
Yes.
Okay, so 2,450 times 10 to the 6, and you multiply this by what?
0.28 meters.
And let's see if you get close to about 300, 300 million. Okay. Let's get some. You guys have phones on you, right?
Yeah.
Okay. Take your phones and let's plug it in, and let's see if you get close to speed of light, which is 300 million. Okay. And know that this is a rough estimate because we didn't really see the center, so it might be slightly off, but let's see. So get a calculator, you guys. Yeah.
I just want to let you know that I had like 12:35, and after that you're going to lunch.
Yeah, got it. So take a calculator and plug in these numbers. So 2,450 times 10 to the 6, multiplied by 0.28.
I got 686 million.
So what did you get?
686 million.
686 million.
2 times speed.
Yeah, 2 times speed of light. I mean, it's not a bad result. We're like maybe a little bit. I mean, we're like double the speed. But again, you have to remember, we're just estimating. We don't know the exact.
Yeah.
I don't see the exact spot either. We're just looking at the center. So it's a pretty good result based on the primitive, equipment that we have. Okay. So look, we got something very close to the speed of light. Yeah. All right. Let's go answer the questions here. Yeah. Let's do the calculations here. Okay. You guys can maybe sit down and do the calculations and write it down. Distance between the hotspots. Okay, so let's write it down. 0.28. Well, it's 28 centimeters, but you convert it later on.
Yeah.
Yeah, but let's do that in there. Let's sit down. And you guys know how to do the percent error? Do you know how to do like? I didn't teach you how to do percent error yet, right? Okay. We'll do percent error. I think we're like 100% off because we doubled the speed of light, but I think it's a okay result. So you can plug in the equation. Frequency of the microwave is right there. 2,450 times 10 to the 6 hertz. And the wavelength is 0.28. So what did you guys think? What did you overall? What did you think about the demonstration?
I liked it.
Yeah?
It's like when you took something like that's really simple that you can easily do at home, like take chocolate and put in a microwave, but then you learn like the science that's behind it. It's not something too complicated, but
Yeah.
like, you learn that there's a lot more to just putting chocolate in a microwave.
Yeah, I mean, now you can say, hey, I know I can find the speed of the microwave, which is the electromagnetic wave. So in reality, you're trying to find the speed of light. I mean, light is also electromagnetic wave. Yeah, good. And what are some sources of error, you think? Because we didn't get exactly 300 million. We got double. So what do you think some source of error for this?
We didn't have exact points of wavelength.
We didn't have the exact points, and also I don't know if how accurate the frequency of this thing is, because like the one that I typically use in my school, it says it's about. Well, actually, let's use a typical. Let's see if it's going to change, because the one that I'm used to in the lab I use, it's 1.25 gigahertz. That's 10 to the 9. So let's do. What would happen if we did this in BSmart in the lab? Do we get a better result? So instead of this microwave, let's use a typical microwave. They're saying a typical microwave is about 1.25. So 1.25 gigahertz. Giga means 10 to the 9. So 10 to the 9. Okay. So let's multiply. Let's see if you use a typical microwave instead of that reading. So instead of this number here, let's put 1.25 times 10 to the 9 hertz. and then multiply by 0.28. They're going to be closer.
I got 98 million.
98 million. 98 million, well, it's
I don't
let's
know.
say 1 million then. 98 million is about, roughly about 1 million, right? I mean, 100
Sorry,
million?
Accidentally add the 0.28 here.
Oh, okay, so what
I
is
got
it?
350 million.
Oh,
Close.
so if you use that reading of a microwave, is what is it?
350 million.
So if we use this frequency of a typical microwave, we actually get a better result. So maybe, I don't know how accurate that frequency is. So what is it?
350 million.
350. That's actually a lot closer than this one. So I don't know. You know, maybe we're better off doing it over there in this one. But okay, all right, cool. We have a few minutes left, right? Okay, so let's do the source of error. If you and since we got a better result with the other reading, let's do the source of error. What's the equation for source of error there? I put it up on the last page. How do you find this, the percent of error?
Measured minus accepted divided by accepted times.
What do we measure if you're using the more accurate number?
350 million
350 million.
divided by probably the speed of light.
Yeah, which
I
is
mean,
the
subtract
accepted
the speed
value,
of light
right?
divided by speed of light.
300 million.
Yeah. We have
And
to
then
subtract 300 million.
yeah,
from
300 million there.
And then whatever we get there, we multiply it by
100. How accurate are we if you're using the typical reading then?
I got 16.666, etc.
16. Did you divide it by 300?
Yeah.
16.6. Oh, percent error. Okay, yeah. That's so. That means your percent error is about 16.6. You said.
Yeah.
Let's say 16.7. So percent error is only. So we're almost like 80% accurate. 20% not accurate. Okay. Yeah, that's not bad. Okay. Any final thoughts? Any reflections about this demo? Would you do this at home? Try to figure out the speed of light at home.
Yeah, because not like everybody at home has the same microwave. So
Yeah.
per se, like if it was a class or a group of us and we all went home and like did it with our microwave, we might get like different percent errors
Yeah.
based on like the frequency.
Yeah, I don't know how accurate, because this one said the frequency before was 2,450 megahertz, but I don't know if that's accurate or if it's always every time when you plug it in, if that's the frequency. But yeah, try it using different frequencies. Maybe you might be more accurate. Okay, we'll call it a day. I mean, you guys have about, how many more minutes you have? We finished it early.
Like 15.
It is about roughly about 15 minutes. Wow. Okay. Yeah, I had that much time. Okay. Oh, you can help yourself to chocolate in that 15 minutes. 'Cause, since you guys had a better result, I'm going to use this for my next demo here. You can go from pieces. If they're solid, you can actually, yeah.
Can I ask a question?
Yeah.
For your last presentation, what was the percentage error?
Actually, that one, there was so little time, and I was rushing to it, I didn't even get to do the percent error. But they got, what was it? Somewhere close to about, roughly about same thing, maybe 600 million, somewhere around there. And it was not as accurate as 350 million. It was pretty off too. I'm just wondering, maybe it's the frequency of this microwave versus
Yeah.
the one that we have over there. Every microwave is slightly different.